All right, so we are starting Unit 10, which is Waves and Sound. And the first part of this unit is Chapter 13, which is Oscillations and Waves. So we're going to talk about oscillations and periodic motion and what those mean. We'll talk about pendulums, what waves are and the properties of waves, and a little bit about how waves interact in this portion. So an oscillation is any kind of back and forth motion that we can kind of talk about that's cyclic, that basically means this has a cycle that it completes. So some examples of this are just simple pendulums in a grandfather clock. So any other motion that repeats itself over and over is referred to as periodic motion. So if we think of like the orbit of a planet, it goes from one point back around to the other point. That has a period of motion. That's a periodic motion. So oscillations going that back and forth are related to periodic motion. So things kind of going in circular orbits. So again, we're going to be talking about things that have periods and frequencies, because we did that with circular motion. So a period is the time required to complete one full cycle of motion. So we're going to be dealing with that in seconds per cycle. Whereas the frequency is the opposite of that. That's the kind of oscillations or cycles per time. And that we call the hertz, which we use a uppercase H, lowercase z to denote. So, in essence, frequency and period are related. That frequency is the inverse of period. So frequency is 1 over t. So some common examples. So if I was to look at the hour hand on a clock, so it takes the hour hand on the clock 43,200 seconds to go around once in that 12-hour cycle. Now its frequency would be the inverse of that. So that would be 2.3 times 10 to the negative 5. We look at something else like, let's say the second hand on the clock. So a second hand goes around 60 kind of seconds for one cycle. That's its period, 60 seconds. Whereas the frequency would be the inverse of that, 1 over 60, or 0.017 hertz. A housefly. So a housefly, its wings might beat 200 times a second. So 200 hertz would be the frequency of that housefly's wings. Now, if I can, convert to find the period, so the inverse of that frequency, that would be 5 times 10 to the negative 3 seconds per oscillation. To start describing these oscillations, the easiest way to do that is by talking about the simple harmonic oscillator. So a simple harmonic oscillator is very simply put a mass attached to a spring. Now the reason we put attached to the spring is we talked about springs with Hooke's law. We have restorative forces. So basically, when that mass is on the spring, there's a equilibrium position that it wants to be at. So we're going to call that equilibrium position 0. Now I can displace it a certain distance either to the right or the left of that equilibrium, and we can call that the amplitude, how much I've displaced it. So if we start the card out, or this mass out, at an amplitude A, so I stretched it to the right some amount A, and I let go of it, well, initially it has no velocity, it's not moving, but it's been displaced. So there's a force on it from that spring, a restorative force that wants to pull it back towards equilibrium. So as it reaches equilibrium, no longer is there a force on it, but it's moving, so it has a velocity. Okay, having a velocity means it has inertia. Mass times velocity is, momentum. Continues through equilibrium and starts heading in the negative displacement, and eventually it gets to a negative amplitude. Stops. Again, that force now wants to restore it back to equilibrium. Gets to equilibrium, moving. Now it's just moving in the opposite direction. It's moving back towards the positive A. Eventually it gets to A. Stops again. So this whole cycle that happens with it going from positive A to negative A and then back to positive A is a full oscillation cycle. All right, and the time that's going to take for it to do that is 1 period, or basically t number of seconds. So to complete each segment, to kind of go from a displacement of A to 0, we take a quarter of that period. To go from 0 to negative A would be another quarter of the period. Negative A back to 0 would be another quarter, and then from 0 to A would be another quarter of the period. So that's the full oscillation cycle that it's doing, going from A to negative A, then back to A. Now we can plot this. So one thing they used to do back in the early days in physics is they'd have a device where you'd have this mass oscillating with a spring, and there'd be some sort of pen or marker attached, and you'd have a roll of paper being pulled behind it at some known rate. So now I could plot that motion with time. And as I plotted that motion with time, I'd get a sine graph or a cosine graph here, where I could see that the time of oscillation would go from peak to peak. The amplitude would be that distance from the equilibrium position to the maximum of those peaks or those troughs. And you could actually study the oscillating motion. Now, the easiest way, though, for some people to comprehend this, because we have this whole idea of it's going from one form to another, is in terms of energy. So when I'm at the extremes, when I'm at A or I'm at negative A, I've got spring potential energy only. When I'm at equilibrium, I've got kinetic energy only. When I'm at any other point in between, I've got a little bit of spring, a little bit of kinetic. So we're just doing conservation of energy here. And I can use that conservation of energy idea along with some of the principles that we understand from circular motion, right? Because circular motion is a form of periodic motion. That I'd be imagining myself going through a period of or a cycle of 2 pi r or 2 pi a as my circumference or my displacement path. And I can derive an equation to understand how long it's going to take. And if I do that, and we will take some time in class to do this, we can find that the period for that oscillation will be 2 pi times the square root of the mass over the spring constant. Okay. The frequency now will be actually the inverse of this. So the frequency would be 1 over 2 pi. Okay, that 2 pi is kind of in parentheses there. Square root of k over m. All right, but right now the main one we're looking at is the period. So period would be equal to 2 pi square root of m over k. A pendulum is also going to have that restorative force on it. And the basic pendulum is just we have some mass, and when we say that mass has some mass of m, attached to a very light string or rod of length L. The mass is sometimes referred to as a bob. If you've ever heard of the term plumb bob, which are used in civil engineering to find a straight line, it's connected to the idea of a pendulum. Now, we're dealing with something here called the small angle approximation, because when we have a pendulum displace, we can only assume that it's going to hold true with these equations for very small angles. So hopefully in math class, you'll get to this idea of what's called the small angle approximation, which is that basically the sine of theta is approximately theta for angles up to 10 degrees, okay? But it's specifically in radians. So the radian value of the angles between 0 and 10 degrees, that radian value is equal to the sine of that angle. So if I did sine of 1 degree, that's approximately the same as the radian value of 1 degree. The sine of 10 degrees is, again, approximately the radian value of 10 degrees. So it allows us to make some math approximations about that restorative force and about the motion here to figure out what the period of oscillation will be for the pendulum. And when I go through and I do those derivations, which again we'll do them in class fully out, we find that the period of the pendulum is equal to 2 pi the square root of L over G. So the period of the pendulum only really depends on the length of the pendulum and the gravity. Now it's an interesting point here, because that means that if gravity changes slightly, the period's going to change. So if you ever looked at a grandfather clock, you'll notice a small knurled nut, kind of looks like an acorn at the bottom of most of those pendulums, that's there to change the length just slightly, like a few millimeters, so that you can adjust for the local gravity. So we know that gravity here in New England might be a little different than gravity at the North Pole, or different than gravity in the Rocky Mountains or at the top of Everest. And you need to adjust for that length to make sure that that pendulum swings at the correct period of oscillation. So now the key piece is, well, why does the length affect it? So to look at this, we set up two kind of pendulums next to each other, give them the same displacement, which means they're going to have the same restorative force, in terms of that angular displacement. But what happens here, if I notice, I've got two different actual values of the length or the displacement they have to cover when they swing. So with the shorter L, okay, the one on the left doesn't have to travel as far during its oscillation as the one on the right does. So the one on the right will have to travel much farther during its swing, even though it's got the same angular displacement, which means it has the same restorative force. So it's like saying that I've got the same acceleration on something, but I have to travel a greater distance. Well, it's going to take a much greater time to travel that distance. That's why the longer the length is, the longer the period is. pendulums and other oscillators in the real world, we can get into this idea of dampening or resonance. So what can happen is you have external forces on the object. So it could be friction that slows things down. It could be some other like tapping or something adding energy that allows things to kind of speed up. So we could have this thing that happens at the natural frequency. So everything wants to swing at a certain frequency or a certain period of oscillation. And if I tap it just right, I can start gaining energy at just the right interval and not lose it, and I get much larger and larger amplitude. So imagine the example of like a child on a swing. You've all probably when you were younger were on a swing, and if your parent or somebody else pushes you at just the right time on that swing, you're going to get going higher and higher and higher. But if they push you at the wrong point, it could actually slow you down, right? So if they push you and you come back to the amplitude, you're going to go higher. But if they push you when you were at the furthest point away, it actually could stop you and slow you down, all right? So that's the idea of dampening versus resonance. If you're being, given that natural frequency, if I push it and add energy at just the right time, you get larger amplitudes. If I don't push it just right, that external force can actually dampen the motion or slow it down. Now, kind of famous example of resonance is something called the Tacoma Narrows Bridge. So what happened with the Tacoma Narrows Bridge was the bridge itself, when it was constructed, had a natural frequency that was just around that of the winds that were going through the Tacoma Narrows. So in the Narrows, they generally had winds in that 35 to 40 mile per hour range daily. So this, kind of heavier than a light breeze, constantly there, but nowhere near hurricane force, that would hit the bridge and kind of tap the bridge. And as it tapped the bridge and tapped the bridge and tapped the bridge, over time it started to make the bridge get this unwieldy motion of rocking and wave-like motion that eventually tore it apart. So now waves. What a wave is basically a disturbance that propagates or is transmitted from one place to another, carrying energy. Now, most waves that we deal with in this unit have to disturb some sort of medium, because we're looking right now at mechanical waves. There are E&M waves that don't need a medium to travel. They just kind of transmit their energy without having to travel through like, gases or liquids or solids or things like that. So the most common, examples we'll talk about things are like ocean waves or sound waves. And then again, those EM or light waves, we'll talk about later on. So it's important to distinguish here that we're dealing with the idea of energy moving and not the particles. So the easiest example to understand this is if you've ever been to a sporting event and you've seen people do the wave. So as that wave moves around the stadium, the people don't move, but the wave moves, the energy of the wave. The people kind of stay in place, just like in a real wave, like an ocean wave. All that water doesn't move. The water just transfers the energy from the atoms, that it's in to the next group of atoms, to the next group of atoms, and just pushes it along. We can characterize this the fact that the particles are actually what are moving, but the wave itself completely moves the energy along. Now, there's different types of waves depending on how we move the particles. So do we move the particles perpendicular to the motion of the wave, or do we move the particles parallel to the motion of the wave? So in this example here, we're moving the particles perpendicular to the motion of the wave. Okay? And when we do that, we call this a transverse wave. So if the motion of the wave is perpendicular to the actual motion of the particles, so basically I've got up and down motion of my particles, but my energy is still moving kind of forward, that's a transverse wave. Now the other type of wave is a longitudinal wave. And in this case, we get like areas of compression and expansion within a medium. So whether it's a gas, like a sound wave, or many liquid waves, like ocean waves, oddly enough, are this type of wave. They're areas of compression and expansion of the medium. Both the wave's energy and the motion of the particles are parallel to each other. Okay, the particles don't travel along with the wave; they're still just moving kind of back and forth and back and forth and back and forth. They're oscillating, but they're in the same direction of the motion. Kind of a side-by-side comparison. Your longitudinal wave is where that medium vibrates parallel to the direction of the energy transfer. The transverse wave is where the medium vibrates perpendicularly to the direction of the energy transfer. So now when waves propagate with the ocean wave, just to kind of give you an idea here, that ocean wave is actually a compression and expansion kind of situation. So there's areas of higher pressure, lower pressure as it kind of moves along, and it propagates outward, which creates those crests and troughs that we see. It's actually not a transverse wave. It's not like the particles are moving up and down. The particles are going back and forth and just compression expansion within the liquid wave. So our parts of our wave, again, are kind of simple. We have crests and troughs. The velocity of the wave will be v, and we have an amplitude of the wave, which we've talked about already. And then there's this kind of concept here called the wavelength. And the wavelength is generally measured from crest to crest or trough to trough. Or it could be the full waveform, the length of one full waveform, which would be one crest, one trough. Where I could kind of almost like cut and paste and just keep repeating it. And we use the symbol lambda. Lambda looks like an upside down Y to represent wavelength. So our amplitudes are where those crests and troughs occur. Okay, and the wavelength again is going to be that consecutive crest to crest or trough to trough, kind of as our general definition. Though we could have it so it's like just a full waveform that again I could like cut and paste and just keep repeating the pattern. So we need to be able to understand what's amplitude, that maximum distance from the equilibrium position, what's the period, so the time it takes the wave to move one full wavelength. Now for the speed, this is where it gets a little interesting. So the speed is generally considered as being distance divided by time. So if we're looking at wavelength and period, velocity of a wave would be lambda over big T for period. But we already know that frequency is 1 over big T, so we can think that velocity is equal to lambda f. And that's like the most common definition for a wave speed situation. V equals lambda f. Like I said before, waves can travel through different types of medium. So we're used to thinking of like sound waves go through air. It's about 343 meters per second. If they're going through water, or liquids like that, could be about 1,400 meters per second. Or a solid like steel could be almost 6,000 meters per second. Okay, so depending on the density, they travel faster. That's why if you look at kind of old Western movies, like they used to put their head to the ground, or head to like the railroad track to see if a train was coming or a stampeding herd was coming, because the sound would travel faster through the solid. You'd hear it before you'd hear it in the air. One other fact with this, though, is that temperature can be a dependent factor. So example with air, cold air, 0-degree air would only be about 331 meters per second, whereas warm air is around 343. So waves can reflect. Most common way people think of reflection of waves gets in with sounds that have like echoes, or like light waves. When you see your reflection in the mirror, that's light reflecting in that mirror. Now, depending on the type of wave you have, you can either get reflection where you have what they call fixed end reflection or non-fixed end reflection. It just means whether or not the pulse, when it hits the surface of reflection, inverts or not. But now when those waves kind of meet, or those pulses meet, we can get something called interference. And you may have talked about superposition of waves, or sine and cosine functions in math class. Basically the idea, you can add sine and cosine functions together. So the same thing's true for any waveform or wave pulse. So if I take two waveforms and they come towards each other and they're in sync, they could constructively interfere, basically make a much stronger wave pulse. Okay, and then they could just pass through each other. If they're opposing, so one's a crest, one's a trough, when they meet, they could destructively interfere. They just kind of cancel each other out, and then just kind of pass past each other and be going on their own way. With interference, you can get interference patterns, which is kind of useful for things like sound. Or if you ever watched ripples in a pond, when the two kind of disturbances of waves meet, they make almost a new wave pattern as they meet. With these areas of constructive and destructive interference. So one of the great applications of that constructive and destructive interference gets into standing waves. So this is how like the guitars and the stringed instruments work. So what happens is you have these two fixed positions of the stringed standing wave, or whatever the standing medium is. And at those ends, nodes have to form. So a node is an area where the wave can't move because it's fixed in place, it's held in place. And in the middle you get an antinode. So the most basic of these is what's called the first harmonic, where you basically have a node, an antinode, and another node. Okay, and in that you're basically only getting half of a waveform. The second harmonic would give you a node, an antinode, a node, an antinode, and then another node. And in that, we get a full waveform. Eventually, you add again, and you get 3/4 of the wavelength in that length of, string or whatever your medium happens to be. So again, the nodes are those points that cannot move. The antinodes are the points that move the most. And they're generally halfway in between two nodes. When I know that there's a certain velocity that a wave can travel at on a certain string or a certain medium, and I know those lengths, I can start to figure out what frequencies we have. So again, those harmonics refer to a frequency. So the first harmonic is normally known as what's called the fundamental frequency. It's the first possible frequency that can set up on a string or a standing medium. The second harmonic is basically twice whatever the first is. Sometimes we refer to this as the first overtone because it's one above the fundamental. The third harmonic will be 3 times that first harmonic or that fundamental frequency, and is known as the second overtone. And again, this pattern will just continue. So harmonics just go kind of 1, 2, 3, whereas the overtone system goes fundamental and then first, second, third, fourth. So if I go through the math and I figure this out, we can get to this idea that the frequency that you'll have in terms of n, which is kind of what harmonic you're at, the harmonic number n, will be the frequency for the harmonic is equal to n times v over 2L, where v is the wave's speed on that string or whatever medium it happens to be creating the standing wave on, divided by twice the length of the string.